I'm Dr. John Mercer, and I'm going to talk about moving exercise science out of the lab into the real world. Now, wearable technology has been around for some time. Here we have a ring that's an abacus. We have one of the original GoPro cameras, another GoPro type camera here, virtual reality, and our classic cell phone. And even heart rate monitors have been around since the mid to late 1970s. So wearable technology is nothing new. However, there has been an explosion of this market due to the miniaturization and reduced cost of producing some sensors that can be worn easily on the body, and the ability to collect data and send data to a algorithm to process and run the data through some different algorithms. These are some companies that are currently engaged in developing wearable technology, and this is just a small number of them. So it's a big industry. Now, wearable technology, what I'm going to talk about is smart electronic devices versus technology that is wearable. Now, smart electronic devices have some type of computing power to it, some type of feedback that's provided to the user, and some type of analysis either during or real time or after completing an event. And these are devices that are typically worn on the wrist, maybe on clothing around the waist area, maybe in the trunk area, or maybe in the foot. But these are all smart type devices that I'm going to be talking about versus technology that you can wear, like glasses or hearing aids even. Now, wearable technology in this category are being used for a variety of issues. One is to monitor physical activity. For example, track the number of steps someone takes, or how much energy expenditure they're having throughout the day, or even monitoring sleep. The wearable technology is also being used to monitor health, where someone wears a device or multiple devices. The data are communicated to health professionals, and information is flowing in this direction, and then also there can be some type of intervention that is remotely activated based upon the data that's being analyzed. And there's wearable technology that's showing up in the workplace in clothing like fire gear, as well as clothing like this, where different devices are embedded in exercise wear. And there are a number of different places that the wearable technology can be worn, and this is just a little cartoon of lots of different places that wearable technologies are built to wear. Now, what I'm interested in is using wearable technology from a research perspective and ultimately moving our laboratory capabilities outdoors. Now, wearable technology that you buy off the shelf generates big data sets, and these big data sets are communicated through smart applications on your smartphone, maybe through web page interfaces, and there's lots of different data points that are provided to the user. All sorts of metrics regarding physical activity and run performance or cycling performance or even swim performance, and even information on training parameters that help someone design a training program or evaluate their training program over time. So these are devices that are generating big data. There's all sorts of sensors that are used in wearable technology. This is a review by Wang and colleagues, and they identified a number of different sensors that were studied as part of wearable technology evaluation. And the number one sensor, the top most frequently used sensor, is an accelerometer. So why accelerometers? Well, the bottom line is, and I'm going to talk about this in more detail now, is acceleration is proportional to force and can reflect intensity and frequency of movement. So let's talk a little bit more about the type of technology that I'm interested in right now. There's all sorts of devices out there where the data are run through proprietary software, and the user gets some type of information based upon some algorithm. I'm not interested in talking about these. What I am interested in talking about are the devices that are wearable and generate data, and you have access to the raw data. And in this case, I'm going to focus specifically on acceleration. So accelerometers come in all sizes and shapes. This is just a picture of a lot of different ones. The ones that are being embedded within wearable technology devices are small, miniature type of accelerometers versus accelerometers that we may use more in a lab setting. Regardless, they're all built on this principle. Here is just a schematic of an accelerometer where we have some known mass as part of the accelerometer and some type of transducer, in this case a piezoelectric material, that changes its electrical properties when this mass is accelerated. And we have sensors, or the ability to sense that change in electrical activity, and hence we're able to measure acceleration. Again, these accelerometers are small. The way that they're built is that they are unidirectional for the most part. They have one sensitive axis. In this example, the sensitive axis is the long axis of this accelerometer. So to get a 3D accelerometer, we need to mount accelerometers orthogonal to each other. Again, from a miniature perspective, this is quite large. The miniature accelerometers are embedded within your smartphones and are very small, but the concept is exactly the same. So now let's get to the tutorial part of the of this session and define acceleration. Acceleration is rate of change of velocity with respect to time. When we graph this out, and I'll be doing that, the acceleration is represented by the slope of the velocity versus time plot. The units of acceleration are meters per second, or we can rewrite that as meters per second squared, or just write it using this type of algebra. The units are also often referred to as G's, and we do that simply by dividing by the acceleration due to the force of gravity. So we divide our acceleration raw signal by 9.8, and we then use the units of G. Kinematic parameters. Acceleration is one of the categories of kinematic parameters that we use right here. It's directly related to velocity and position. And in fact, when we do the math behind these, position is simply displacement, change in position, velocity is rate of change of displacement, and acceleration is rate of change of velocity. So really what we're doing when we're looking at these three categories of kinematic parameters, when we're going in this direction where we use position data to derive velocity data, and when we use velocity data to derive acceleration data, we're taking derivatives of each parameter. We can also work in the other direction where we can start with acceleration data, we can generate velocity data, and then use those data to generate position data. And when we do that, we're taking the integral of this parameter to generate this parameter, taking the integral of this parameter to generate position data. It's all based upon these formulas right here and easy to manipulate in a algebraic sense. So we can go in either direction here. So we have lots of measurement options, and the two main categories that can be used out in the lab or outside the lab include camera-based systems and GPS system to monitor position, and then use these data to generate velocity and acceleration data, or accelerometers on this end, and then you can generate these data going in this direction. The downside of using a camera-based and GPS data-based system is that the magnitude of noise that's in the position data gets magnified exponentially as we generate acceleration based upon derivatives. Likewise, over here, an advantage of using accelerometers is that the force is proportional to acceleration, and we use that to try to get an understanding of categorizing how intense exercise is or how much movement there is outside. So here we have a direct connection to the kinetics of movement. It's just the trick is understanding what this acceleration is all about, and that's what this part of the tutorial is about. And there's two important characteristics that I want to cover in the rest of this presentation. That is the direction and magnitude of acceleration. Now each of these parameters are vectors and are represented by magnitude and direction, and I want to focus in on those two aspects of acceleration now. Now, when I do this type of lecture in a undergrad or even a graduate biomechanics class, I'll start with a question like this. If you know that acceleration of a projectile is negative 9.8 meters per second, which is common knowledge, can you tell me which way an object is moving, either up or down, if it's a projectile? So here what I have are three plots. These are all vertical direction plots. This is vertical position, vertical velocity, and vertical acceleration. Time on each axis, on x-axis. And here we have acceleration, here velocity, and here position. So here I've plotted out acceleration, 9.8 meters per second squared. It's negative. That's just the acceleration due to the force of gravity. And if I ask you, given this acceleration, is the object moving up and slowing down, or is the object moving down, speeding up, or something in between? And the fact is, you can't answer that question without some information about velocity or position, and so there's no way of knowing. So here's what the velocity and the position data look like if we start a projectile at a low point, throw it up in the air, and have it return back to this low point. The position data will look just like this. Velocity data will look like this, where the velocity of the object is slowing down while moving upwards and speeding up while moving downwards. Acceleration is maintained at negative 9.8 meters per second squared, which is the slope of this line right here. So if I ask you again, what's happening with position data given a negative 9.8 meters per second squared acceleration, it could be the object is moving up, it could be the object is moving downwards, or it could be something in between. So the acceleration being negative 9.8 meters per second squared, the magnitude of the acceleration is 9.8 meters per second, and the direction is negative. And the only thing this negative acceleration is telling me is that the slope of the velocity versus time plot is negative. It could be that I'm moving upwards and slowing down, or moving downwards and speeding up. So the bottom line here is direction of acceleration does not indicate direction of motion. So that's take-home point number one of my part of this presentation. Direction of acceleration does not indicate direction of motion. Same concept, negative 9.8 meters per second squared. Without knowing something about the position of the object or the velocity of the object, I can't tell whether or not the object is speeding up, going downwards, or slowing down, moving upwards. All right, so now we're going to get to take-home point number two and work our way towards that and talk about acceleration magnitude. The magnitude of acceleration represents how quickly velocity of the mass is changing. Mathematically, it's the steepness of the slope. So here, if I have a positive acceleration, I have a positive slope in the velocity versus time plot. And a greater acceleration simply means a greater slope. There's greater change in velocity over a shorter period of time. Hence, magnitude of acceleration is greater. All right, so now what I want to do to try to work into understanding that magnitude issue, I'm going to show a series of videos, and then I'm going to show you the acceleration. And right here, the accelerometer is mounted on this bowling ball. And all I'm going to do is pick up the bowling ball and drop it. And so in your mind, just envision what that acceleration profile looks like. I'm doing this task on top of a force platform right here. I put a little cushion here so it doesn't do crazy damage to my force platform. All right, so here's the task. The ball drops and rebounds a bit, and I'm measuring the acceleration throughout that task. This is what the acceleration looks like. This is time on this axis, acceleration in units of g on this axis, and the acceleration is 0 to begin with. Then I drop the object, then the object hits, it undergoes some acceleration. It rebounds. This is negative 1 meter per second squared, or negative 1 g. Rebounds, and so forth. So it's bouncing, and eventually comes to a rest here, again, 0 acceleration. Now I did this on the force platform, so here's what the force tracing looks like. This is force on this axis, time on this axis, 0 force to begin with, and then we have forces going up to 700 newtons, then it goes down to 400 newtons. This is rebounds, it's in the air here again, it's 300 newtons, and then it's sort of coming to rest on the force platform at this weight. So, how are these things related? Well, they're perfectly related by Newton's second law. And this is Newton's second law. Some of the forces acting on the object cause that object, the m, the mass, to accelerate. Well, the forces acting on the object are ground reaction force, or the force of the ground pushing on the object, and the weight of the object, which is acting downwards. So gravity is trying to pull that object downwards. Well, if I just rearrange that equation, I can calculate my ground reaction force if I know the mass of the object, if I know the acceleration of the object, and if I know the acceleration due to the force of gravity. Here's the acceleration of the object. I measure that with my accelerometer. I know the mass of the bowling ball. I put that in here, and I get a curve that looks exactly like the ground reaction force. It's perfect. In fact, it double checks that Newton's law is correct, and I can understand the forces acting on this object if I measure the acceleration of the object. There's a little disagreement here, but that's because the accelerometer is actually measuring the acceleration of the object in this region here, where it's initially not on the force platform, and so there's no way of the force platform to measure that acceleration. All right, so here's another task. All I'm going to do is pick up this foot and stomp down on the force platform. The accelerometer is mounted vertically on the distal aspect of the tibia, and it's wrapped quite tightly with a Velcro and elastic strap. All right, this is what the task looks like. So I'm standing on the force platform with both feet. I'll show it again. Just a very simple task. And this is what the acceleration profile looks like for what I'm calling a leg tap. Acceleration on this axis, time on this axis. We see a very definitive spike. Then we also see something negative happening here, and then something else going on here. This spike is upwards around 10 to 12 Gs, or 10 to 12 times the acceleration due to the force of gravity. I did this on the force platform, so let's look at the ground reaction force. This is what it looks like. Standing on the force platform, body weight, and then I pick up the leg and I stomp down on the ground, and I see forces of around 1600, just over 1600 newtons, and then I'm standing still. Again, this is body weight at this time. So let's see how these two are related. And I'll follow the same model I did before, Newton's second law of motion. The two forces acting on the object are ground reaction force and weight pulling down on the person. And if I rearrange the equation the same way, and I plug in the mass of the person of 82 kilograms into this equation, and I use this acceleration profile, if I do that math, my predicted ground reaction force is now this red curve here, which yields about a 9,000 Newton force. The peak ground reaction force from the force platform is down in this region, around 1,600 newtons. So what's going on? These don't match up, where they did match up for the bowling ball example. Let me do one more example. This is what I call my finger tap example. I put the accelerometer on the tip of my finger, and all I'm going to do is tap on the force platform. That's it. Just a simple tap. Okay, let's look at that acceleration profile. And this is a 3 tap, so it doesn't actually match up what my video showed. I just cut that down. Here's acceleration on the y-axis, time on this axis, and each one of those finger taps yielded an acceleration of around 60, almost 70 times g. All right, I did this on the force platform, so let's look at the ground reaction force. Here it is. Here's force on the vertical force on the y-axis, same time axis here. And okay, so ignore the thick blue line. Look how low these forces are. This is 40 newtons here, 45 newtons. It's very typical that a force platform will have plus or minus 5, maybe plus or minus 10 newtons of noise. And that's what this thick band is. This is just noise. But you can see these distinct peaks right here, which correspond with each finger tap. Well, now I'm going to do something a little different than what I did before. I'm going to do the same, use the same Newton's second law, use the same algebra here, but instead of putting the mass of the person in here, I'm going to put in the mass of the finger. I'm not going to put in the mass of the entire person, which is 82 kilograms. I'm going to put in 53 grams, not kilograms. I got to fix that. So I'm going to put in 53 grams, all right? And now I'm going to calculate the force based upon this acceleration profile and using this mass. And I'm going to zero in on the middle peak just so that it's a little easier to see. Here's the ground reaction force derived from the acceleration profile, and it matches up quite nicely with the ground reaction force and yields a peak force of just over 30 newtons. But here the trick is I used effective mass, or used mass of the finger as opposed to mass of the entire body. Okay, so this is getting to take-home point number 2, effective mass. Effective mass is the mass that is being accelerated. Now we know acceleration magnitude is proportional to the force, but proportional, it's equal to the force when we know the mass that is being accelerated. When we know the mass of the object that's being accelerated, we call that effective mass. When it's a segment of an entire body. So for my finger example, the effective mass is only the mass that's being accelerated, which would be the mass of the finger, not the mass of the entire object, or in this case, the entire person, being 82 kilograms. I was able to figure out quite easily the effective mass of the finger, but that's not always easy to figure out, and sometimes we just don't know what mass is being accelerated when we're doing whole body movements. And this is an important point. We do a lot of work on leg acceleration during running, and this is a very characteristic leg acceleration profile. Well, here you see these peak accelerations, which are characteristic for each foot strike, run about 6 Gs. Whereas with the finger tap, I was showing Gs of up to 60 or 70 times G. Well, something just doesn't seem right here. Well, the difference between running and doing a finger tap is the amount of mass that's being accelerated. When I put an accelerometer on the leg and I'm running, the mass that's being accelerated includes probably most of the lower extremity and maybe some of the upper extremity. So we need to know what this effective mass is to really understand the link between acceleration and forces. This is the acceleration due to the segment moving. That is indisputable, and it can be very useful information. However, we need to be very careful when we're interpreting acceleration magnitudes and when we start talking about forces, because the link to force is only done through knowing effective mass. So take home point number 2, effective mass. If acceleration magnitude changes, for example, when we run an experiment where we compare shoe 1 to shoe 2 and we look at leg accelerations, or if we look at slow speed versus fast speed, we have to know that the acceleration signal can change if the effective mass of the signal of the person changes versus the actual acceleration of the segment changing. So it's important to consider effective mass during each condition. When effective mass is small, acceleration can be high for a given force. Finger tapping, for example. Very low effective mass, very high accelerations. I'm not going to get hurt doing a finger tap exercise like I would landing from a jump or running with a stiff lower extremity. All right, so to summarize this part of the tutorial session, the 2 main take-home points that I wanted to hit on is direction of acceleration does not indicate direction of motion, and effective mass is important to know. And when we're looking at acceleration profiles, when we place accelerometers on different parts of the segment, we can understand acceleration is proportional to force, but it's only equal to force when we know what the effective mass is. And effective mass can change between conditions, and it's not always clear how much effective mass there actually is. Okay, thank you.